The particle, according to quantum mechanics, is both decayed or not decayed. If the particle decayed, the cat's going to end up being dead. If the particle does not decay, the cat will be alive. And so the question is, if you're not looking inside the box, then is the cat a mixture of both? And so that idea is, does this quantum mechanical paradigm, if it's related to our real world, our macroscopic big world, does it also bring that same paradigm to us as well?
Welcome back to Out of the Box podcast, where Steele and I, Jose, your host, get to talk about outside of the box ideas. And for those who are new to watching our podcast, this is a podcast that is geared towards bringing out interesting topics in the world. We like to bring in people from different sectors of studies. And today we have a special guest here with us, Dr. Lombardini. Did I mention your last name right?
Lombardini.
Lombardini.
It's like Lombardi, but has an extra ni at the end. So Lombardini.
Lombardini. Yeah. So thank you for being here with us.
Sure.
Really appreciate you being here. And Steele, if you want to touch up on some of the intros.
Yeah. So Dr. Richard Lombardini is an associate professor of physics at St. Mary's University in San Antonio. Dr. Lombardini got his Ph.D. in physics at Texas Tech in Lubbock, Texas, after getting a bachelor's degrees in both mathematics and chemistry, also at Texas Tech University. And then Dr. Lombardini pursued a postdoctoral fellowship in computational chemistry and physics at Rice University in Houston, Texas, under the guidance of Dr. Bruce Johnson. His prior research is in wavelet functions and computations and theoretical calculations involving nanophotonics. And Dr. Lombardini's most recent research interest is in quantum field theory, something that we might dabble into a little bit here. So I wanted to jump into that. So tell us a little bit about your work on formalisms and possible physical interpretations of quantum mechanics beyond the traditional Hilbert space structure and the Copenhagen interpretation. And then kind of like, as we were talking earlier, before we get into that, if you could kind of give us and the audience a basic idea of what quantum mechanics is.
Sure. Yeah. So let me just start off a little bit with the basics of quantum mechanics. So when somebody says quantum mechanics, I mean, a lot of people get very excited about that. And basically, it is a theory on how things in the microscopic world behave. When we're talking about things like atoms and molecules and even smaller subatomic particles, which would be like neutrons and protons, and even smaller than that, you can break down protons and neutrons into constituents called quarks. So when you get to that level, when you look at those things at that level, when looking at that small, those kinds of objects at that scale and really, really small, the normal physics that we think of, which we call Newtonian physics, okay, what we experience, it doesn't work anymore, it just fails completely. And so there needs to be a new theory. And so in the early 1900s, a lot of people found that this Newtonian stuff is failing for these microscopic situations. And so this theory developed called quantum mechanics. And there's a lot of weird things in quantum mechanics, a lot of strange things that happen. I would say, one of the weirdest things I would think is the fact that particles, which we think of like electrons, you think of a little ball in space. Electrons particles can have wave-like behavior as well as a particulate behavior. We call that kind of the wave matter duality or particle wave duality or something like that. And so these different behaviors can manifest in different situations. And that's a very bizarre thing because, we know what a wave is. If you think of light You think of microwave radiation. You think of radiation from your cell phone is in the form of waves. And then you think of like a baseball, and that kind of acts like something that's concentrated in space. And you think to yourself, well, how could something exhibit both of those properties? Well, in quantum mechanics, very, very small particles do exhibit both of those qualities. And so that's kind of one strange feature in quantum mechanics. Another one I think that is probably, or an area of quantum mechanics, which is the actual physical interpretation of what is going on, when we're not observing something. The traditional interpretation that is adopted by physicists in the community, or has been adopted for many, many years since the beginning, is known as the Copenhagen Interpretation. And what that means is that you can represent a quantum system, which could be an electron or two electrons, or however many particles you want. You represent it with something called a wave function. Okay, and the wave function, and so basically, it's as the I guess the term tells you, there's a wave-like property that you're introducing into your system. Now, what is weird about this wave function? Well, first of all, one of the good things about it is this wave function is what we call deterministic. That's good because we like determinism. What does determinism means? Well, determinism means that you can predict the evolution of something in time. You can predict it using equations, and so it's something that can be predicted. Like, so if I have a baseball and I throw it, I can use Newtonian physics and the equations, and I can determine exactly where it would be at any time point after I throw it. Okay, so one of the good things is this wave function is deterministic. There's something called the Schrödinger equation. It can be used to determine that the wave function, which can represent your system. And so the problem is, how does the wave function represent your system? Well, it only gives you probabilities of your system. Okay, so for example,
and when you say your system, are you saying like the human system, or
I'm
just
talking about
anything?
like a microscopic system, like an
Okay.
electron or something.
Mm-hmm.
Okay, so let's say you have a wave function and it represents an electron. Okay, and let's say, for example, you want to measure where the electron is at some position. All right, in some position in space. You would, in classical or in Newtonian mechanics, if it was like a baseball, you could use the laws, Newton's laws, and you could figure out exactly, and you knew all the forces that were acting on that baseball. You could use Newton's laws, and you could find out exactly where that baseball is. Okay. In quantum mechanics, you don't have that. You have this wave function that represents your electron. What is that? And that wave function only gives you probabilities of where that electron is. All right. Now, that probability, like I said before, you can predict the probability at any point in time. So the probability changes as time goes on. All right. But it doesn't tell you exactly where the electron is. It only can tell you information on probabilistically where it is. You can calculate averages of where that electron could be. So basically, if I were to, I guess another way to explain it is if I had 100 identical electrons, they were all identical, and I gave them all this, they are all experiencing the same conditions, the same forces, they all had the same initial conditions and same environment and all that stuff. Well, what would happen? Well, classically, okay, or Newtonian thinking, if they were identical, they should all be in the same spot after a certain time period. Well, that doesn't happen in quantum mechanics. What happens is you will have the electron you'll find the electron in different spots, in different spots, even though they're completely identical. And you do this experiment over and over and over with identical electrons, you're going to get different positions of where the electron is. And so, what
is
does
that because? Yeah,
Mhm.
is that because they at some point start exceeding different wavelengths, or going on different?
Well, the reason is, so there there are many. So that's where I think people are puzzled. Okay.
Mhm.
If you were to go back into the Copenhagen interpretation, and this is something that was developed by one of the pioneers of quantum mechanics, Niels Bohr, and he's a famous Danish physicist. And if you were to ask him, of course he's dead, but if you were to ask him, he would say because what that wave function basically it represents the electron kind of smeared over a big region of space. So the electron is basically this wave that's smeared over in space, and it actually is kind of in every position.
Mm.
It's basically present when you're not observing it. It's basically present in all these different has all these different possibilities, and they're all possible, meaning that it exists in all those places, and there's certain probabilities, okay, that it will exist. So it's just kind of smeared out in space. Once you observe the electron, that wave function collapses, they say, and you will find the electron in one spot.
Mm.
All right. And so the question is, well, if you were to do this, let's say you had 100 electrons and you were to let it do its thing, and you measured these 100 identical electrons, you get these different spots. Well, if you kept having more and more identical systems like that, you could get an average of where the electrons you would find those electrons. You could calculate a good average, or you could actually measure it in the lab. You could measure an average of where you would find that electron. Now, you can actually calculate that average using the wave function. Okay, so the wave function could give you things like where you would, on average, find the electron. It can tell you that there's a 30% chance of finding this electron at this position, and there's a 50% chance of finding it in this position. And there's things like you can use that, and that's all you can calculate. So there's this you only can calculate the probability of where the electron could be. And the question is, well, so that's the conundrum. So Einstein, you always hear that Einstein had a big problem with quantum mechanics. Well, Einstein would say, well, there's got to be something missing if this wave function only allows us to calculate the probability of where some object could be. Okay, so Einstein had a problem with that. And in fact, Einstein thought that perhaps, and this is something that's not known as much, but he thought perhaps that wave function actually represented what he'd call an ensemble of particles, so a bunch of identical particles. So it represented, and so it was actually a statistical thing, and we do that a lot, or like we call it a distribution function, and we have distribution functions in a field called statistical mechanics, and so it was something that was heard of. It was, so like in statistical mechanics, you may have a container of gas, and there's probably a massive number of gas particles, like 10 to the, let's say, 23rd, a mole of gas particles in there. It would be stupid to just go in and figure out what every gas particle is doing and then using all that data to predict, like, let's say, the pressure of the gas. That we won't have computers for. We don't have the ability to capture that much information and analyze it like that. And so what people in statistical mechanics do is they use statistics to kind of give you these averages and things like that, and to calculate pressure. And so Einstein was thinking that perhaps the wave function is doing something of that nature. And
so almost to say, like, like the elements have electrons, right? They're composed of almost the same material, and so if we're trying to figure out one electron, what is there to say that we didn't find another electron, right? Just because they're the same components. Is that kind of what he was having trouble with, kind of deal?
So you're saying, well, it was more that what he was I guess what he was really having a problem with, that wave function would represent one particle. It could represent one particle. And yet in the end, when you calculated that wave function at a particular time, you could only get the probabilities of where that particle would be. And so, and his thought was, well, then you're incomplete. The theory is not, there's something missing.
There's not, if it's only probability and not really like the defined like location, then what is there?
Exactly. So he's like, maybe we don't have the theory figured out completely. Okay. And so another thing is he didn't like was the fact that the observer was what determined or had to play a massive part in the actual position of that particle. So it's a very odd thing. So let's say when you're not looking at the electron, when you're not measuring it, it's this particle, is this big cloud of possibilities. Okay, that's what the wave function is. And then once you measure that electron, you find it in one spot. Okay, so it's actually the observer plays this massive role in determining where the electron is. And Einstein was like, well, I don't like that. Why does the observer have to play in the reality of the electron? Why can't the electron have its own reality independent of the observer? And that was another thing that he had troubles with.
Yeah, that's what I wanted to talk about, actually. Yeah, because
it's how we affect the quantum world, right?
Yeah.
And didn't that come from the double-slit experiment where there's multiple lines, like an interference pattern or something like that? Even though there are two slits, it still made a pattern of parallel lines or something, right?
So with the double slit experiment, that's a great experiment, and it's something that a lot of people talk about. And yes, that demonstrates a problem. So what it is you have these two kind of openings, and you send an electron. And today, physicists do have technology to just shoot one electron at a time. Okay.
Wow.
Okay. And so usually it was like a beam of electrons, but now physicists, even one photon at a time now. So there's this amazing technology that has been developed in the past years, which has allowed physicists to actually look at the stuff, these questions that they've had in the past when the quantum mechanics was being developed. But anyways, so let's say they can, in the double slit, they can send one electron. And what happens is, the idea is that electron, if it's just a particle, then it should be able to, it's going to either pass through one or the other of the slits. Okay. And then in the end, they have a screen at the very back that the electron hits. And once the electron hits it, then you know where the electron is, because that screen kind of tells you, or lights up where the electron hits. And so that's the observer. That would be the thing that would cause, that screen would cause the, I guess you could say, that wave function to collapse at a certain point. So if the electrons acted as just little points in space, like what we think of like baseballs and ping pong balls and things like that, then you would find a pattern where you would have some electrons traveling through the left slit and some traveling through the right slit. And you would see that, right? But what happens is something completely different. What happens is you get these patterns, like you said, these long lines of patterns, and basically they're just strips that contain lots of dots in it where electrons hit. But you have these slits, and so there's some regions where the electron never goes, and then there's regions where they do go. There's a lot of them that hit, and they alternate. So you'll have a very bright slit with lots of electrons hitting, dark. Then you have another bright slit, dark, and so it's kind of like they're alternating. And what that looks like is a lot of people will look at it and they'll say, well, that looks like an interference pattern. Okay. Waves wave can interfere with itself and create a pattern where you have constructive, destructive, constructive, destructive interference patterns, just like what you see with the electron. And so the idea was, well, then that means that what if the electron actually is this kind of permeated wave in space? And then when it hits the double slit, actually, some of the electron goes through one of the slit and some of the electron goes through the other, because it's this wave permeated in space. And then that wave can interfere with itself and produce this interference pattern. Okay. But the thing is, so where does the collapsing happen? Well, when the interference pattern hits the screen, is then you get a dot on that screen. Then it collapses into one point. And those dots, what they find is those dots start forming a interference pattern as if it was a wave. So there's this kind of this mix of two things going on, wave and particle duality. And so the idea is this, perhaps this electron actually is this kind of wave that is permeating space. And then when it hits the screen, it collapses into one position. But the pattern that is produced is as if it does confirm the fact that the electron had to kind of go through both slits at once and interfered with itself. And so there's a lot of weird things going on in there. And that actually led to this idea of this wave function basically representing a mixture of where the electron is. Okay. It's not really, yeah. Go ahead.
And is the particle, would you say that a particle is the same, like an electron is producing waves, or is a wave?
Is a wave, yeah.
Is
a wave itself.
So it's a wave. Yeah. It's like a wave and a particle at the same time as well.
Yeah, it's got both properties.
Real mystery.
But then when it collapses, it turns into the electron.
So once you observe it, once you measure it, it collapses into one little position.
Okay.
The big mystery to me is the observation idea, because a big question I've had for a while is I have a hard time wrapping my head around that part.
Yeah.
Because it's interesting how, like, is it more of what we're measuring? Are we measuring reality wrong? Like, it's not our technology isn't advanced enough to measure what's really happening? Or is it something like we do kind of influence reality with measurement or observation or something else in the measurement process? That's a strange.
Yeah, there's two thoughts on that. Number one would say that when you are measuring something, you are interfering with the system. So, for example, if I want to observe something in a microscope, okay, and let's say we're in the really small scale, we're looking at electrons. The act of me trying to look at it, that I have to shoot a photon at it. Okay, so what light we know can act as discrete little packets of energy. We have to shoot something, and that just by shooting a photon at it, that will affect the electron itself. It'll give it some momentum or do something to it. All right, and so that act of actually measuring does change the system. So there's that kind of thought. Although I think that in the Copenhagen interpretation, as far as I understand, it just collapses. When in the observer's, I guess, behavior is a little more mysterious than that. Niels Bohr, if he was alive today, he would just say, well, this gives us the right answers. Get probabilistically, obviously, gives us the right answers, and that's good enough. Okay. I think now a lot of physicists are saying, no, that's not good enough. I mean, if you can think about in history, okay, if you go back a ways where you had the Ptolemaic versus the Copernican view of our world, right? The Ptolemaic view was that the Earth is the center of everything, and the Earth is stationary. And Copernicus was like, well, no, I see that the sun is actually kind of, well, in our solar system is kind of the center of our solar system, and things are orbiting around that. Now you could make I guess you could make a model, mathematical equations based on either one of those interpretations, and you could probably still predict things. Okay. Obviously, we know that the Copernican view is correct. That gives us the best reality. And so really in the past, physicists have been interested in reality. And so it's very odd that a lot of people in quantum mechanics are not really interested in the reality of what's going on.
The reason
they're just saying, hey, this theory gives you the right answers.
Yeah, we have the answer.
Right. It gives you, and that's a big problem with quantum field theory. Okay, this is something. Quantum field theory is okay. So basically, you have quantum mechanics, and you also have a theory of relativity. Okay, let's do special. There's general, but let's just move. Think of just special relativity. And special relativity, basically is a new way of dynamics when things go really, really fast. Okay, we're talking approaching the speed of light. The speed of light is 3.0 times 10 to the 8 meters per second. So when things go really, really fast like that, you get some weird behavior that happens. Okay, you'll get length contraction, and you will get things in something called time dilation, where the frame that the clocks move slower when they're moving moving faster, and things like that.
Is that why they say like black holes kind of like morph like physical things? Like, when in the movies they go into a black hole and then they twist the aspect of like reality, just like things are bending and just
because light itself gets bent into black hole. So if you can imagine, light itself can be bent in a black hole, that can really distort reality in a sense.
Does gravity, is it the gravity of the black hole and because I think from what I remember, it's like the greater the mass, the greater the gravity kind of thing, or
the more mass, the stronger the gravitational.
So is that to say that gravity affects time in some way?
And gravitation also, yes, and this is measured in labs nowadays.
Right.
Gravitational fields do affect time, how time.
Right.
And you watch the movie have you ever seen the movie Interstellar?
Interstellar.
They did a great job in that, because if you were on a planet, and in part of the movie the Matthew McConaughey and the other two people, I can't remember the names, but they were on a planet that was near a black hole, and their time moved much slower than their friend who was on the ship that was further away from the planet. And so their time scales were moving differently. The people that were on the planet near the black hole, there was a very strong gravitational field, and that was distorting time. So that has to deal with general relativity. So that's kind of going beyond. But in special relativity, we don't incorporate gravity in that. But anyways, it just says that things that move fast, there's some weird stuff going on. So anyways, they've combined quantum mechanics and relativity together, and this studies small microscopic things that move really, 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 really fast. And they created a field called quantum field theory. But in quantum field theory, it works, meaning they can get right answers, but then they have to break rules in doing it. For example, when they do the calculations, some of the terms in the calculations are infinite. They get infinity, and they just go, well, we just throw them out. Okay, well, we just throw them out. And you're just like, why? What's the reason? And there's not a really good reason as to why you throw them out. And another thing is quantum field theory. It also kind of gives a picture of where there's these things called virtual particles that are involved. And what are virtual particles? Well, they're particles that, do they exist? Well, I don't know, but they can have negative energies. You can have virtual photons, which have mass. Photons aren't supposed to have mass, but you can have virtual photons. So it kind of bends the rules in this virtual world, and yet that's the kind of picture it provides. So there's a lot of problems with quantum field theory in that it doesn't follow a mathematical, rational or logical scheme. It breaks those rules, and also it gives a picture that it just doesn't make sense. But it does give, when you follow the rules that they figured out, it does give you very accurate calculations that match well at the particle accelerators. And so a lot of scientists are like, that's good enough. Okay, for me personally, I want a more, we would say, ontological or more physical, realistic picture of what is going on. And so there's another kind of I guess interpretation of what is going on with reality, and it's called Bohmian mechanics. It was developed by a guy named David Bohm in the 1950s, and he said that, and he developed the math, and it became the math actually gave you the same answers as with the traditional quantum mechanics that has been used in the Copenhagen interpretation, all that stuff. But this time, there are two things that are at play. There are actual particles in Bohmian mechanics. So an electron is actually a particle, and it actually travels in a path. Okay, that's beautiful, right? We all like that. That's what we're all interested in. The weird thing about Bohmian mechanics is there's also a wave. So for every particle, there's also a wave, and they call it a pilot wave. The wave kind of guides the particle, and it gives that particle its weird quantum behavior. Okay, and so that's kind of another. It gives you the right answers, but it's another viewpoint of reality. And so
is that why they say like it's a wave and a particle? Because
wave and a particle,
the particle is going along with the wave, so it represents the wave, but at the same time it's the particle.
Actually,
right? Because of the movement.
It's weird because, what is the wave and the particle one thing, and they're just different manifestations. It's actually I think in the theory, people think that they're separate, and so the particle is the wave itself has information on like forces around it and properties of the particle itself. So it does have some things about the particle, and that wave guides it. It actually provides forces to give it the path that it goes along. And so that's kind of, I think it's a better direction, because now you have a real particle. It's got a real position, and it doesn't need it. You don't need an observer to determine where it's at. You can, where it's at, even if you're not looking. So the great thing about Bohmian mechanics is you don't need an observer. Okay? It tells you where the particle is at every point in time. It's just, the weird thing is you now have this wave. And what is this wave? Well, I think there's a lot of mystery in that, but this wave actually gives guidance to that particle, and you need that wave, and it gives it the particle's weird quantum behavior. And this way of doing things can reproduce the same experimental results as the traditional quantum mechanics that you learn in your quantum mechanics course. Okay, so it actually works quite well. It's a lot of people don't like it. I don't know why. Well, there's some things that are debatable, or some things that are distasteful, I guess. Number one, I think the one thing that I think a lot of people express dismay about it is because although the wave affects the particle doesn't necessarily affect the wave. So there's this not mutual interaction, which happens in like, let's say if you had an electron and electromagnetic wave, the electron itself, when it accelerates, can give off an electromagnetic wave, and in itself can also be affected by an electromagnetic wave. So in all our other theories, we see this reciprocity. There we go. That's a tough word. Anyways, you see that, but in other fields of physics, but not necessarily in this. So, I've been studying Bohmian mechanics, and I've been studying with my former PhD advisor. His name is Bill Poirier, and he's at Texas Tech University, and he is a phenomenal thinker when it comes to this stuff. Now, he's a chemical physicist. He is really interested in looking at how to solve reactions, like chemical reactions, quantum mechanically and exactly, because you got molecules and atoms and they come together in reactions, and these things obey the rules of quantum mechanics, not Newtonian, but they're very hard to calculate. In fact, if you add an atom to your molecule, your computation goes up exponentially. It just gets more and more complicated with quantum mechanical theory. And so you have this problem is you don't have the computational resources to calculate reactions or even just motion of molecules and atoms with many electrons or molecules with many atoms. You don't have the computational resources, or nobody does, to do accurate calculations using the traditional quantum mechanical theory. And so he has found many ways, many tricks to alleviate that. And I spent my PhD doing that. But the reason he is interested in Bohmian mechanics is because that may also provide a way of reducing the computations needed in doing these types of calculations in this formalism. So he's really interested in Bohmian mechanics because of that. And there was a guy. Oh, go ahead. Yes.
So, for example, whenever like physicists are trying to figure out like the exact position, you know, I guess the big question is like, why would someone want to like figure out the exact position? Does that help, you know, build things, or is it more just for the theoretical aspect to think about, almost like philosophy, to think about, oh, this is essentially where it would be, or does it have some practical aspect to it? I'm sure it does, right? But
I think it's very practical. I mean, if you can use equations to model exactly what particles do in certain situations, okay, this could lead to massive technological advances. I guess, you know, if you were to develop
quantum technology.
if you were to, yes, and quantum technology has led to things. For example, TVs.
Time traveling.
You know, Samsung has I think it's called a Q. I was looking for TVs recently, and they have this QLED screen, and it uses principles of quantum mechanics.
Wow.
To give you a richer assortment of colors. What it uses is something called quantum dots, and quantum dots are little pieces of usually some sort of semiconducting material, some material that is kind of in that property, semiconducting, very small pieces, and they're like about 100, let's say 100 to 1,000 atoms. And because they're small, there's a lot of properties, quantum mechanical properties that it exhibits. And one of them is that they tend to, based on their size, they tend to emit certain wavelengths of light. So you can make quantum dots. If you make quantum dots certain sizes, you can control what sort of light they emit. Okay. It's quite interesting. And it's a quantum mechanical principle. And so the more you know about quantum mechanics, the more you know about how things behave in those rules, and the more you can model it computationally, I think the better we are. You could actually develop, you could model different types of circuits, and you could see what sort of thing you could get, and you could do that instead of going into the lab and actually developing it, which would take lots of time and resources. You could, if you knew the behaviors of all the components very well, and you could model them with mathematics, you could use a computer and say, oh, if I did this and this is what would happen. You wouldn't have to go and actually get the equipment and put it together, and so it would actually cause technological advances to move faster.
That reminds me of what I've heard. They're trying to work on quantum computers to do something like that, right?
Yeah. So quantum computing
is just to make computational functions much faster.
Yes.
Who knows what we could learn with that? I mean, it would just solve a lot of things.
Yeah. So quantum mechanics in itself, even though it's hard to calculate with our computers today, it may itself serve an answer by developing new technology in computational technology that could speed up the computations even faster. And so then maybe you could even model more complicated systems that you couldn't model before using quantum computers. And that's a big field. right now, what I'm interested, I'm on a sabbatical, and I'm interested in Bill Poirier. He got, I was telling about Bohmian mechanics, right? It's got its pilot wave. It's got a particle that actually has a trajectory, and then there's actually a wave, which actually turns out to be the wave function that guides that particle. Well, he found out that when you fiddle with the math, and he found out that you really don't need the wave anymore. And he published a paper in 2010 and showed that you don't need the wave function. In fact, you can just calculate, if you do some mathematical manipulations, you can actually get these equations that you can solve, and gives you a trajectory, just a trajectory of the electron, and you don't need any wave.
Wow.
Okay. So now the question is, well, and then if you, so what you can do is you have this equation that gives you this trajectory, but you can have different starting points of these trajectories. So you can actually calculate a whole ensemble, or a big, large group of particles. Let's say you had a bunch of electrons and they're all in different positions. You can calculate their trajectories together.
Wow.
And so
do you like, this is something I was just thinking about. I'm not sure if it was if it's possible, but I think about it like the idea of quantum mechanics. It almost sounds, and I don't know, I don't want to say it's exact just because I haven't done too much research into it, but it's almost like new life in our modern world, right? When you have a baby, the baby represents all possibilities, right?
Mm-hmm.
But it really comes down to the people around them to really focus and tell them like, hey, this is what you need to do. This is where you need to go. And so it's almost like the observer plays a part in the baby's, future. Right. And so I almost wonder like if quantum mechanics almost has an effect on our trajectory, and if so, are people able to manipulate that trajectory based on external aspects? Maybe like, I don't want to bring in the government, but like maybe like somebody actually notices that this quantum mechanics also applies almost in a real scale to us being kind of like particles in this universe. Yeah, almost to bringing it to the Newtonian level, if it has any aspect. It maybe, I don't know if it's subconsciously, or maybe it's something that is affecting us, because if it can affect us in a subatomic level, just but we're composed of several atoms, then is that aspect exponentially produced?
So this is a great question. So this is the same question that Schrödinger, in a sense, have you ever heard of Schrödinger's cat?
Yep.
Schrödinger actually thought of this. I think, if things like this happen at the microscopic scale, how does it affect things at the macroscopic, our scale, like the big scale, right? And Schrödinger devised this thought experiment. And I don't know if you've heard of it. Is the cat dead or alive? Okay. So the idea is you have, on the microscopic scale, you have a particle, and by quantum mechanics, according to the rules of quantum mechanics, it can be both. The particle can both exist and have decayed. It can be both. Okay. It can exist or not decay, and it can decay. All right. So it can have both possibilities all at once. It's once you look at it, once you observe it, then you will see it's either decayed or not. But quantum mechanics says that when you're not observing it, it's a mixture of both. So suppose that you have that, and it's attached to a device that is connected to a box. Okay. And inside the box, you have a cat. If in this device will release poison into the box, if the particle decays, and will not release poison in the box if the particle does not decay. Okay, so and the question is, so if you have this device and you're not observing the particle, and therefore that particle is kind of in a mixture of both decay and non-decay, then the question is, if you're not looking at the cat in the box, is the cat in a superposition, we would call it, of being alive or dead? Is it both a mix? Okay. Does that make any sense?
Yeah, is it dead or alive? It could be.
Is it dead or alive?
So
If you don't look at it. If you don't look at it, right? Because the particle, according to quantum mechanics, is both decayed or not decayed. If the particle decayed, the cat's going to end up being dead. If the particle does not decay, the cat will be alive. And so the question is, if you're not looking inside the box, then is the cat a mixture of both? And so that idea is, does this quantum mechanical paradigm, if it's related to our real world, our macroscopic big world, does it also bring that same paradigm to us as well? Okay, so that was a big thought experiment. Now, I don't know if anybody's done this, right?
Is it almost like the idea of like, if a tree falls in the forest, did the tree really fall? Or
so that's the whole idea of does the observer play a role in the existence of something, in the existence of even an event, right? Like you say, if a tree falls and nobody sees it, it doesn't really fall, right? That's the question. Does it produce any noise if there's nobody to hear it? Okay. I firmly believe it does. I don't think an observer needs to be present for those things to exist. I think they can exist without any sort of observation and just can happen on its own. But that is a philosophical question, which does seep into quantum mechanics. And quantum mechanics says, well, if you're not observing it, then it's a mixture of many possibilities. The tree could fall and could be not and could not fall, or something like that, if you were to the macroscopic world.
So in terms of like, I'm guessing this also like seeks into like things like, for example, like musicians when they're improvising, the possibilities of them improvising in a certain way, or like playing a certain note or doing something. It also, I guess, in a way comes down to quantum mechanics. Does that ever seep into like consciousness, like their ability to create
all that stuff?
Yeah,
that's a great question. I've heard of some people talk about the possibility that there is a quantum mechanical kind of theme in consciousness, and especially in the formation of thoughts. Okay, in particular, so if you may have a thought, or in your prefrontal cortex, you may abstract different possibilities in your mind, but the question is, well, which possibility do you choose, right? And there's a lot that goes into that. And could it be that those possibilities, they all exist in your mind, obviously, and the question is, well, how does that I would say wave function that represents all, how does it collapse to one choice, right? How does it collapse to that one choice? And is there anything guiding that collapse to that one possible choice, or is there, is there some sort of probabilistic collapse, things like that? And that's, that I don't know. That
what leads into like multi-universes.
So that's another thing. So a lot of people believe in something called the many worlds hypothesis, and this is also due to quantum mechanics. Instead of being a wave function that represents many possibilities, what if there's just so it's an independent observer. So you have let's say an electron, and it actually does move in space, but But when you actually measure it, or some sort of quantum event happens, you have these different possibilities, but you only see one. But the other possibilities happen in parallel universes. Okay. Or you could say that I think Sean Carroll is a very well-known physicist who promotes an idea that every time a quantum event happens, you get a splitting of in two worlds are being created, and they're parallel. And so, do you choose to eat a hamburger today, or do you choose to eat spaghetti? Well, if that's a quantum event, then when that happens, that decision is made. You split into two parallel universes. That is another thought.
Is that how they try to? Was that ever tied with free will or something like that? I thought I remembered reading something like that.
Yeah, I mean, it could relate to free will. because in free will, there's many possibilities that could happen. What makes you choose the one? Well, what if different worlds spring up, and so in each world is a different possibility that you have chosen, and so we are only conscious of one world, okay, even though other worlds are being created.
It's almost like in the movies, they have one world where it's like everyone's evil, right? Because if we in this world are choosing good, then the opposite decision of that would be choosing evil, right? So that whole world is distorted into its own.
Right. You could have many worlds. You could have many parallel universes going on, where all of these choices that are being made are actually being made. All the possibilities are actually being made. You just create different universes. What I'm interested, what I've been studying is in Bill Poyer's work on let's throw away the wave function, and so what he has found, what his equations that he has derived has found, is something called a possible interpretation is many interacting worlds. And so what does that mean? It means, well, he thinks that, well, we created a particle in our world that has a definite position and a definite path. But in many parallel universes, there's and a lot of universes are very close to ours and some are very far apart. But the ones that are close, the universes that are pretty close to ours, similar to ours, they also have these electrons moving, but their path is a little bit different. Okay. And in the particle in one world and another particle in another, in a neighboring world, you could say, there's actually some interaction, and that causes the quantum weirdness that we see. It's the fact that this particle that we're measuring is interacting with particles in other universes that causes this weird quantum effect. Okay, and that's what the equations kind of point out.
They almost interact. Is that kind of like saying like kind of like the consciousness or ideas kind of exist, and so is that maybe why some people have a eureka moment, because in another universe they already thought about that?
Oh, it could,
that
just
could
be a possibility, right?
And is that how they could interact?
It could. I mean, that could be I guess a result of that idea is that, a lot of times it is very funny when you get good ideas, they come out, or when people are inspired, you hear about artists, you hear about writers, and then you ask them like, where did and a lot of times they'll just say, it's just like there's a muse, right? There's some transcendental kind of experience that they can't explain, that, and the idea just pops into their brain. And yeah, you're thinking of, well, if there's many parallel universes, and then could one of those universes affect the other universe, right? Somebody in one, let's say you are in another universe and you're geared towards this great idea, and so all your environment helps you create that. But then in another universe, you don't have the conditions for that idea, but somehow you in one universe affects the other, and so then this information gets passed. I mean, these are some possibilities, I guess, that you could say with many interacting world picture. Yeah. Now, has this taken off? Some people are very interested in the mathematics of this, because it eliminates the wave function completely, which is something that has puzzled people for forever. And so the idea, but how really in science, the ultimate golden standard is, well, can you devise an experiment that would thus prove that this interpretation is the right one? And so far, we haven't really thought of anything that could be done. And that's the golden standard right there in science. But it's still fun to think about, and the equations actually do work, and they do give you the right answer. And so, so you could even Bill Poyer, I think, is mostly interested in, does it give you a mathematical framework where you can do calculations easily, more easily than you would in the more traditional framework, so that you don't need as much computational power, or you can do problems that required computational power beyond what we can provide. And so does this new mathematical formalism give you a way to do calculations that you couldn't otherwise do? So, he's mostly interested in that, although he does speculate about this many interacting worlds kind of idea popping from the mathematics. So it's quite interesting.
That is interesting. Yeah.
Wow.
Yeah.
It reminds me of Albert Einstein's spooky
action at a distance. Yeah. So Einstein, there was something called the Einstein Podolsky-Rosen paradox, EPR paradox. And in that, basically it talked about quantum mechanics allows two things to be entangled. Like you could have two particles and they are entangled. So they're either created. One example of an entanglement would be like if you had one particle and it released it decayed into two particles. Well, those two particles are entangled because they've come from this one joint body. And the question is, in Einstein, or according to quantum mechanics, those two particles are part of one wave function. Okay. And so whenever you do something to one particle, it automatically affects the other particle because they're entangled. They're in this one wave function. And, in quantum mechanics predicts that this can happen, this entanglement can happen. And so if you measure this one, automatically this one changes. And so the reaction is faster than what the speed of light would be if they were exchanging information. And Einstein didn't like that. He was like, no, nothing can travel, not even information can travel faster than the speed of light. And so he was very worried. He didn't like that, and therefore, him and these other two scientists developed the EPR paradox, which later was challenged with an Irish physicist with the last name of Bell, and Bell devised something called the Bell's inequality, and basically it was a way of testing whether the EPR paradox was correct or not, and so later on, once the technology developed. People found that, well, the EPR paradox actually, there actually is entanglement and there actually is this instantaneous change. And people have been able to do this, entangle photons, and then they measure the photon here and the other one is affected instantly. And so it actually does happen, and so.
Really amazing. That just.
No, it is.
And isn't it like the particles could be several distance away? Like.
Oh, yeah. I don't know what the record is right now. I know that scientists are trying to see how far they can get.
Push it. Yeah, that's so cool.
Yeah.
Wow.
Now we've actually verified it with experimental.
Yes, it's actually been verified. Yeah, absolutely. That to me is crazy.
It is. It really is. That's why I'm so interested in it.
Yeah. What the many interacting worlds interpretation of that could be is that you have these two particles, let's say, in one world that are very far apart, and perhaps in another world, these two particles are closer and they can interact. And since information can travel between the two worlds, maybe that's what could cause this. And so, you could use the many interacting worlds to explain it. Although, you have to really to develop the true physical reality. It's going to take a very clever experiment to do that.
Definitely. That's a hard thing to measure. I couldn't imagine.
Yeah.
I'm wondering what technology could be produced with something like that, knowing that this particle here can change this particle over here whenever you do this here. Yeah.
Because I'm already interested, I'm already like boggled by the fact that we have Bluetooth and AirDrop and how even just the fact of like
radio
speaking over the phone, like you can hear me like in a part of the world and we can see each other.
Amazing. Wi-Fi. I guess the particles interact in such a way that they're able to have this invisible kind of pattern that transmits or something like that.
Yeah, you can.
And supposedly they had something like that, right? Like the pyramids supposedly had like an internet connection or something like that.
Yeah.
Maybe that's another.
Who knows? I don't know, but I'm not sure what sort of technology the Egyptians did with the pyramids. Who knows? But technology is just going to get better and better. There was this thought that we were hitting this kind of limit as far as computational speed and processing speed and all that. But with the advent of quantum computing, that's just going to be completely shattered.
I think quantum computing is going to lead to a huge, major industrial revolution, but for technology.
Yes,
Yeah.
I think it will lead. I think so.
That would be the next revolution.
Well,
I think it will too.
Yeah, because it makes me think like, what if another interacting universe has already created quantum mechanic technology that is so advanced that now they found a way to actually come into our universe.
And they created the holographic universe, which is another theory.
Right. Then you have that. Right.
And the atoms are actually the matrix, or the pixels of, no, I don't know. I'm just
I know you can get into all sorts of interesting questions but yeah, I think you're right. I think quantum computing, which, by the way, I mean, they've already developed like IBM and some of the national labs have already developed some prototype quantum computers.
Wow.
That can, so it's already become a reality. Now they haven't eventually, it's definitely not on the commercial scale, but I bet that's not too far away, and it is going to change things, and it's going to change things. I think first it's going to change things in cybersecurity. I think it's going to be big in that. But I don't know. I would predict probably in 10 years. I would say in 10 years we can buy a quantum computer with that kind of technology.
We'll get to see it in our lifetime. That is.
Wow. Yeah, I would definitely.
At the rate we're going, yeah.
Oh, absolutely. Yeah, nice. In all of our lifetimes, I think we'll see it, and I think that will be a very big, a game changer. We will be able to store a ton of information in such a small region of space, and also process that so quickly as well. And it's just gonna, who knows what the possibilities are with that? I mean, who knows?
Like Star Wars, like you have a little like chip on your finger, and you just tap it, and you can see all your documents, and I don't know.
Exactly. Who knows?
Yeah.
Awesome.
So, well,
yeah.
Is there any last thoughts?
Yeah, I wanted to ask, is there anything else you want to share on the research, or kind of like where the research you're doing is headed, kind of thing?
Yeah, I mean, in particular, what am I doing? I'm examining. So there's another phenomenon that is definitely a quantum mechanical is spin. Like particles have spin, right? And people will think, well, does that mean they're actually spinning? Well, we use that term spin, but really it's not spinning. It's something else. So particles carry a type of we call angular momentum in it. It's just kind of like in it. It's built in it, as if it was spinning, but it's really not spinning. And in quantum mechanics, they've been able to theoretically introduce that and accurately and all that. And I'm trying to right now, what am I doing? I'm trying to figure out how to incorporate spin into this many interacting worlds kind of picture without wave functions and things like that. And so that's kind of what I'm looking at right now. And so I've been spending the past month reading and thinking and taking lots of walks and learning all sorts of advanced mathematics. It's enjoyable. But it's tough. It's really pushed me to the limit. And I've enjoyed it. And so hopefully, I don't know, we'll see if I can make any sort of progress this semester.
Yeah, trying to show that relationship. Yeah.
Mm-hmm. Yeah.
Is there somewhere where like somebody might be able to see the end results of your research, or
well, I'm hoping, if I make some progress, if I figure out something, I'm hoping I can publish a paper where, I don't know. I mean, that, you always based on the material and what you find out kind of just tells you where the best journal is. So I'm not sure, but it will be, if you look on St. Mary's website, if you look me up, if I do publish something, I will hopefully.
Yeah, that'd be cool. And maybe, who knows, in the future, when we publish, we can get you back on to talk about the
yeah, that would be great.
Awesome.
Absolutely.
So my only other question in our last 8 minutes or so is, me and Jose talked about this. You know where I'm going, Jose, when I say the fourth dimension. So if there's a fourth dimension of time and we go outside the fourth dimension, does that mean we're outside time? Like, as if there's no beginning or end. It's just eternal. I don't know.
Mhm. Yeah. So that's a great question.
That's almost a whole podcast in its
And I'm
That's
not
a whole
trying to do a bunch.
own.
So multiple dimensions beyond the four have been thought about quite a bit when people were dealing with how to bring together quantum field theory. Okay, that field theory is actually very successful, or another term of it is the standard model, and then gravity. Okay, this gravitational force is very mysterious. I mean, it's what is going on there is actually is space being bent by mass and all that. What is going on there, and in those in the attempts of combining those things. One of the theories you've probably heard of is string theory, and so they and in string theory they've had to introduce some extra dimensions, okay, in those. And the question is, does time in those extra dimensions, does time have any sort of effect? I'm not sure about that. I haven't studied string theory. I haven't really gotten there. I'm still trying to learn quantum field theory. I'm maybe behind in the game. But I don't know if those extra dimensions that they propose, if time has a effect like it would in the three dimensions that we're familiar with. I don't know. I don't know how the dynamics of the dimensions work in string theory. They were able to raise it to, I don't know how many dimensions. I think a total of 11, I think, or something like that. And they were able to say, okay, now the math seems to work, and we see things come together. What does that mean in reality? I don't know. That's a great question.
How do you translate the math into reality?
Yes, exactly. That could be tricky. Yeah.
Very much.
Nice.
Yeah.
Well, thank you very much, Dr. Lombardini. I think we got some really good insights into what quantum mechanics is, and really look forward also to see what else comes up from your research.
Sure.
Yeah, we'll be happy to have you on again at some point.
Yeah, absolutely. Thank you for having me. Yes, I would love to come back on. Thank you.
Awesome. Thank you. Hope you have a great day.
You too.